Now let us go into our class. I hope you remember where we are actually standing. That is our chi-square testing, right? A small introduction, or I'll start with a questionnaire if possible. Uh, Chi-square testing, t-testing, right? Can you say the difference in a single word? Chi-square testing on one end and t-testing. What is the similarity between those two, both? So let me explain the difference. If you want to say the difference between chi-square metric and t-test metric, the single thing is mean. T-testing goes with the mean, right? It will take the deviation with respect to the mean. I'll be calculating the error bound around the mean with respect to t-test. When it comes to chi-square testing, element by element deviation I'll be taking, and based on that deviation I'll be saying the metric, right? This is actually the case. Let us revise the first question and then we'll complete the problem too. We are actually standing in chi-square testing. We will finish off this chi-square testing topic by today's session, right? So what will be actually given? We'll be given some observed values, and we need to estimate whether these observed values are as per hypothesis or not. How we do that, whether it is as per hypothesis or not, is we'll be having some expected values. What is that expected values? Is nothing but there is an expectation for every distribution for a particular sample. For example, if here the observed values for throwing a dice is given as uh, one came and two, three, four, which number turned up? So rarely I get six, all the six number to turn up. If it is a six-ended die. Now, how many times each thing appeared is considered as a frequency, and in the observed values, it is given that 25 times 1 it is obtained, 29 times 2 is obtained, only 19 times 3 is obtained, 36, 32 times 4 and 5, and 27 times 6. Like that, we got a value. Right? This is an observation being done. Now, what we have to do, whether this observation is as per hypothesis or not, we have to see. What is that hypothesis? That is whether the observation are is on par with the expected values or not. For example, how should the expected values be is nothing but if I throw a dice, the probability for a particular die to turn up is 1 divided by 6. One of you said the answer during the last time itself. If I throw a die, the probability for 1 to appear is 1 by 6, the probability of 4 to appear is 1 by 6, and so on. The probability of the particular number to turn up is 1 by 6, an uniform distribution. So, but here the numbers are not uniform. Anyway, we need to check whether they are the deviation is in the acceptable range or in the rejection range, that we have to see. Now, what I have to do is now I take the cumulative frequency, that is total frequency I take, that is add all these frequencies together, and I get 168. From this 168, I say that each thing have to be obtained with a probability of 1 by 6. So 1 by 6 times of 168, 1 will appear. 1 by 6 times of 168, 2 will appear. 1 by 6 times of 168, 5 will appear, and so on. So everything is uniformly randomly distributed. So I get this as an expectation that every number will turn up 28 times as my expected value. Now, what I have to find in chi-square testing is whether these observed and expected values are in the acceptable range or in the rejection range. For the same two things, that is, I can consider it as a t-test also. That is, I have given two different ranges. This is frequency 1 and frequency 2. And I can take the deviation between their own means and I can apply t-testing also. In chi-square testing, I don't care about the mean. Why? Because I take the individual elements. So what I will do is, I will first understand what is the hypothesis. In question, the hypothesis is given as the dice is a fair die. That is fair die in the sense, even though the number of frequency is actually not same for all the numbers, the die is fair. It is not actually biased. And alternate hypothesis, the opposite of null hypothesis, says that the dice is unfair. Now we need to prove that if there is an alignment between the observed and expected values, then the null hypothesis is accepted. If I say the null hypothesis is not accepted, then automatically I can say that the alternate hypothesis is going to be accepted. So this is what the case. So what we will be doing, I'll be enumerating the observed values, the expected values. Observed values represented as O, expected values represented as E. Now what I will take, I'll be taking observed minus expected. That's what the values I obtained here. Next, observed minus expected, the whole squared I take. Why I do this is, the chi-square distribution formula is observed minus expected the whole square to the denominator e divided by e. This is actually the chi-square distribution formula. So for using this formula, I calculate these two things, I obtain it, and I sum it over all the observed values. I get the value 6.1427. So what are these actually called as? These are actually the squared deviations between the observed and expected values normalized by the expected values. I repeat again, this is actually the deviation between the observed and expected values, the square of the deviation between observed and expected values normalized by the expected values. So these deviations I accumulate and I get a value 6.1427. Now, can anyone say the number of samples here is 6? What will be the degrees of freedom in chi-square testing?
5, sir.
Great. That is n minus 1, 5. Great. So for the 5 degrees of freedom, now what I have to take is I have not given any confidence interval. So what I can take is the significance level, the best significance level can be between 0.01 to 0.05. I can take values between these two. These are the best significance level. That is 99% confidence to 95% confidence you can have. So I take 99% confidence, that is 1 minus alpha 0.01. So for phi in 0.01, I go to the chi-square table, and this is here. And for this phi, I need to understand where my confidence interval actually stands. So it actually stands in phi and 0.01. It actually is 15.09. So I go to my value. I see here, I get a value like 6.1427. So what I do a plotting here. This is my plot, and in the plot it says that after 15.09, there is comes my red region, which is not in the acceptance region. It is a rejection region. But I get a value something like 6.149, which is very much before that 15.09. So I accept this particular hypothesis. So that if the null hypothesis H naught is accepted, it means that the dice is Faraday, right? The dice is Faraday. So this is actually the question which I already seen. We have just recapped the things.
Sir,
Sir,
Yes.
sir, what is the use of null hypothesis and alternative hypothesis, sir?
Yes, very good question. I'll explain that. So null hypothesis is nothing but null hypothesis is actually set based on some assumption. Hypothesis is nothing but an assumption. That first I'll say the difference between null hypothesis and alternate hypothesis. What is null hypothesis is whatever is given in the question you accept without any changes. That is actually the null hypothesis. If you go to the question, you get the observed values like 25, 29, 19, 36, 32, and 27. A real time observed values when you throw a die. And this by seeing itself we can immediately say that it is not a uniformly distributed die. Why? Because in uniform distribution all the numbers should have the same frequency, because probability is 1 by 6. But we can, in real time we cannot assure that all the times the same uniform probability will be achieved. So what we have to do is we need to say that whether this die is a fair die or not. Fair die in the sense I can make some bias, I can put some sand on the dice and then throw in such a way that one particular number alone turns most number of time. That is actually called as bias. If I include some bias in the die, it means that the dice is not fair. So I said that without any changes, this observed values and expected values are closer. There is no bias, I'm saying. So in question, it is given that dice is fair, which is null hypothesis. And the acceptance or rejection of null hypothesis can be done in two ways. One is chi-square technique and other is T technique. I can do that. What is alternate hypothesis is the direct opposite of null hypothesis is alternate hypothesis. So what the theory says? Theory says that if you prove that null hypothesis is accepted, it automatically proves that alternate hypothesis is rejected. And in the contrary, if null hypothesis is rejected, it automatically says that alternate hypothesis is accepted. So ultimately what it means, whatever you say in the null hypothesis, it is opposite to alternate hypothesis. If null hypothesis says that dice is fair, then alternate hypothesis says that dice is unfair. So this is the thing. Now without any changes, what I will do, I'll just observe, accept my observed values. I say that the dice is fair. and the numbers may be different. Why? Because it is real time, right? That is the thing I say, right? Now coming to here, this is the thing. Now I get another question. In this question, what we are actually currently solving here, a qualification is given and a marital status is given. The qualifications are eliminated here, and marital status is present here. Now, the hypothesis given in question that you have to prove is whether marital status is going to affect this qualification or not. It says that there is no relationship between marital status and this particular qualification. There is no relation. That is what the hypothesis says. If the null hypothesis says that there is no relationship between marital status and the qualification, then alternate hypothesis automatically says that yes, there is a relation between marital status and qualification. Right? What is the question given? If a person is never married, 18 people are in middle school, 36 people are in high school, 21 are in bachelors, 9 is in masters, and 6 in PhD. Right? If you see, if you ask master's degree, those who have married are having master's degree to the maximum level. Those who have married, they only are having PhD also to the maximum level. So that and all, we have to say whether there is a relationship between marital status and middle school. Null hypothesis, that is what given in the question is, null hypothesis says that marital status and qualification are not related. That is null hypothesis. Then what automatically alternate hypothesis says? Alternate hypothesis says that there is a relationship between marital status and qualification. So that is the thing. So in question you will be getting only up to this. Now you are calculating this total frequency on both ends, right? This is a different case of problem. Rather in the die problem, you use the probability. If you see here, in the die problem, you have given the probability 1 by 6, and based on that, you calculated the expected values. But in a two-dimensional table, like this, if you have, in this table, you need to calculate the expected values in a different way. How you will be calculating is, if I want to calculate this never married and middle school, this particular value, then I'll calculate that with respect to 39 into 90 divided by 303, right? 39 into 90 divided by 303. Similarly, how will be calculating 36? 36 will be calculated as 90 into 90 divided by 303. In this way, I will be calculating this particular values. Now, can you say how can I calculate this 36 expected value? That is expected value of married to master degree. Can you say how to calculate this?
57 into 150 by 303.
Great. 57 into 150 divided by 303. So in this way, we have completed finding the expected values and we kept it here. Right now, we have done all those calculations. The thing what we need to verify is if I add these all, I need to get the same values. I need to get these same values. Why? Because these are expected values, but the total frequency should not change. That is actually the case. So let me verify it. I'll open the calculator. So 11.58 plus 26.73 plus 24.95 plus 16.93 plus 9.801. We get 89.99, and if you see in the observed values, it is actually 90. So it is actually 90. Similarly, I'll just verify it. 19.3 plus 19.3 plus 44.55 plus 41.58 plus 28.21 plus 16.33. I get 149.97. And what is in the observed? It is 150. So it is, since we have decimal values here, it is rounded up, right? The third row, 4.24 plus 9.80 plus 9.14 plus 6.20 plus 3.59. I get 32.97. I hope it is 33. I hope. Yes, it is 33. So the final one is 3.86 plus 8.91 plus 8.31 plus 5.64 plus 3.26. I get the value 29.99. Hope the observed value will be 30. Yes, it is 30. So the value is 29.98. That is 30 again. Right? Are we getting the same values here? Can you verify and say? In the same columns, are we
Yes,
writing this? Yes. Is it same? Have you verified? Will you put the values as it is? Have you verified? 7.58 plus 19.30 plus 4.24 plus 3.86, which give me 38.98, that is 39. 26.73 plus 44.55 plus 9.8 plus 8.91 is 89.99. Wait, 24.95 plus 41.58 plus 9.14 plus 8.31, that is 83.98. 16.93 plus 28.21 plus 6.20 plus 5.64. It is 56.9. 9.801 plus 16.33 plus 3.59 plus 3.26 will give me 30. Yes, it is greater. So we get the values, we verify these total values. Now we can go into the chi-square distribution table, right? I go to the chi-square table. What will be the chi-square table? Can anyone say? Observed. What will be next?
Expected,
Great. Next,
observed
observed,
minus
expect,
expected,
O minus E. O
O
minus E
minus
the,
E whole square,
okay,
O minus E whole square by
O
E.
minus C whole
great. We need many columns, I think. So. This is observed. O, get E. O minus E. O minus E the whole square. Set. So this will be O minus E the whole square divided by E. Now we got that. Now these are the individual frequencies. We need to take all the frequencies one by one. So we can take in this way or this manner. Let us all 63 will follow the same values, right? We'll be following row by row. Okay. I'll start with the values like this. Right. If I was missing any values, please help me. Okay. 11.58. What is the next value? 26.73. Sorry, these are expected values. I'm sorry. These are expected values. So let us finish the expected values first. Okay. Or can you do the one needful? Can you take screenshot of this and say me what is the uh, observed values one by one from 18 to 33? Can anyone do that? Shall I go down? Yes, shall I go down? Yes, please be unmuted. Don't make me to shout, please. What will be the observed values? First one. What is the
18,
first
sir.
observed?
18, sir.
18. Next,
36,
36. Next,
21, sir.
yes, 21.
9, sir.
Okay, 9.
And then 6, sir.
Next, all the things we have to write. We have to write all for all the 20 items. Next, that is 12, 36. Everything we have to write. So you take screenshot and then say me. Can I do? Can I go down?
Yes, sir. 12. The other one is 12, sir.
Just continuously say.
12, 36, 45,
Only 12, 36, 45,
36, 21,
36, 21,
6, 9,
6, 9,
9, 6,
9, 6,
3,
3,
And the next one is 3, sir.
Again 3, yeah.
Yes, sir. Again 3.
Okay, next.
Again 9, sir.
Again 9.
And again 9, sir.
9, 9,
6, 3.
6,
And 3, sir. 6 and 3.
6, 3, 6, 3.
Yes, sir. Sir, 1 minute, sir.
Correct, huh?
Sir, only 163, sir. Not the other. Yes, sir.
That's all, huh?
That's all, sir. And the next one is 39 and 90, sir.
Again it's 39, 90, yeah.
Yes, sir. 39 and 90.
So that is not, so you don't include this.
Sorry.
These are the
Okay.
total,
Sorry, sir.
total
Sorry,
not
sir.
needed.
Sorry, sir.
Now expected values we have here, some for some time we can write. That is 24.95, 16.93, next 9.801, next 19.30, 44.55, 51.58, 38.21, 16.33, 4.24, 9.80, 9.14, 6.20, 3.59, 3.86. Can anyone say, can take screenshot of this and say to me? 3.86, 8.91, 8.31, 5.94. 3.86 next. Right? What is next? 8.91. 8.91, 8.31, 5.64, and 3.26. Yes, we have written all the observed and expected values. Now let me do an easy task here. Now let me take this entire thing and copy it in Excel so we can complete this formula operations easily in a quicker manner, right? Because it is obvious. Can I do that in Excel? So I'm having these things. Now I just take the difference, that is 18 minus 11.5. I get the difference, and similar difference I need to calculate for everything. Yes, I just do the calculations. I got all the subtracted values. Right? Will I increase the size of the font? Or it is okay?
Okay, sir.
Yes. Thank you for replying immediately. Next, I 1 minus e the whole square I need to take. So this will be equal to 6.4 into 6.4. That is whole square. Take that. The similar calculation I follow it for the entire table. Yes, the same thing I do. Next, o minus e the whole square divided by e. This is o minus e the whole square. This is e. So o minus e the whole square, that is 4.21 divided by this 11.58 e. I take that. I get 3.55. I just do the same thing. We should also round it. I round it to 3 decimal digits. I round off to 3 decimal digits. I say yes. So I get the total values. I just take the summation of this and I do. Since you are not going to operate in pen and paper, you also can use Excel. So I get the total value as 21.952, right? 21.952. I am making it clear how to calculate this. This observed values is taken from the question. Expected value is calculated by S, and we take observed minus expected. Next, observed minus expected the whole squared, and I calculate observed minus expected the whole squared divided by E. This is what we calculate, right? Am I making it clear? So far, so good.
Yes, sir.
Yes, sir.
Right? So I get the value 21.952. Let me substitute, put these values in my word also. I got the values here. So let us go down and see. Now I get the value 21.952. I need to check whether it is in the accepted region or in the rejection region, right? So what we have to do? I need to find what is the degrees of freedom, right? So don't say immediately. Think and say what is the degrees of freedom. Now, if you see the table, you can say that how many values are there in the table? There are around 20 values. And if you see the properties, what is given, that is married, unmarried table, you find only 5 values here and here. So that is 4 values here and 5 values here. Now, can you say correctly what is the degrees of freedom? We know that degrees of freedom is n minus 1. That is very clear. But now we need to say whether it is going to be the n value is going to be 19 or n value is going to be 4 or 5. So can you say what is the degrees of freedom? You can see the chi-square table also, and then you can do some decisions. I say that is in chi-square table also we'll be getting some information about the degrees of freedom. So what will be the degrees of freedom? Whether it is 20 minus 1, 19, or it is going to be 4 minus 5 or 5 minus 5 like that. Yes. So that is actually something different here, right? This is actually a two-dimensional table. So you don't take either 4 or 5 are going to be 20. So what you have to do is, so what is the dimension we have, right? First I will write dimension of the data is equal to 4 into 5. Am I right? This is actually the dimension of the data, which will give me the 20 records. Now, when is going to be the degrees of freedom, you take 4 minus 1 into 5 minus 1. One complete row I am actually leaving it out. So 4 minus 1 into 5 minus 1. So what will come here? 3 into 4, I will get 12. Right? I am making this very clear. You don't take either 20 minus 1 or it is going to be 4 minus 1 or 5 minus 1. It is actually a cumulation. You take the dimension of the data. This question is not similar like the dice question, where only one dimension is there. But here there are two dimensions. In the first dimension, I have the marital status, and in the second dimension, I have the qualification. So what I have to do in both, I have to reduce 1. That's why I say 4 minus 1 into 5 minus 1, I get 12. Right? Am I making this point clear, very clear?
Yes,
Yes,
sir.
sir.
Yes. Now going to the significance level. Well, here also significance level is not given, so we can directly go for our own significance level. So what is the best significance level we say? Significance level alpha.
0.01.
Great. 0.01 to 0.05. That is from 99% to 95% you can take anything. Right? So I said significance level is not given. So we take alpha is equal to 0.01 because 0.1 to 0.05 is acceptable, right? Now I go to the chi-square table. You see degrees of freedom is going to be 12. Significance level is 0.01. And I go into the chi-square table. This is a chi-square table. Degrees of freedom 12 is here and 0.01 is here. Now I highlight this entire portion. What is the value given? 26.22. 26.22 is over here, right? Now you are going to check whether it is going to be accepted or rejected, right? Now 26.22 is here. Now what is the value we obtained over here? 21.952 is actually our value, and what is actually given here? 26.22, right? Now I said, right, you can take the significance level between 0.01 to 0.05. If you take 0.05 significance level, I get the chi-square value as 21.03. In that case, 21.95 is greater than 21.03 and it will be getting rejected with a significance level of 0.05. With the significance level of only 0.01, it gets accepted or rejected, whether I can accept this or reject this.
Accept.
Yes.
Accept, sir.
Yes. Yes. Finally, I got some answers. Yes. So I take in the 0.01 range. So I'm saying commonly, if I didn't give any significance level in the question, the default significance level what I ask you to take is 0.01. But theory says that between 0.05 to 0.01, if you take anything, it is correct. To maintain some commonality, we'll be having 0.01. So the chi-square value for df is equal to, df is degrees of freedom, df is equal to 12, and alpha equal to 0.01 is, you go and see in the chi-square table, it is 26.22. Yes, 26.22. And I say that which is greater than, what is my value, 21.952. 21.952. So it is actually greater. So when I go into my distribution table, I just draw it. Yes, I draw it. Now the distribution says that 26.22. Anything above 26.22 is going to be rejected. I say that it is going to be here. That is 26.22. And here alpha value is going to be 0.01, that is significance level, or the confidence range I can say it is going to be 99% confidence, 0.01, and this is going to be my red region. So anything that comes here I will directly reject. But my value actually comes over here, that is 21.95.
So it means third standard deviation, right? 22 for 26.22.
No, here there is no way to consider about the standard deviation. Only in t-testing we consider standard deviation. Here we don't consider the standard deviation at all. Here the thing is individual element deviation. How each element is deviating from the individual element. But between 21 and 16.33, how many deviation? Between 3 and 3.59, how many deviation? That is what we take here. So what I will do here, I can accept or reject. I do the accept. So the null hypothesis says that there is, in the question I say, the null hypothesis says that there is no relationship between marital status and qualification. So that the chi-square testing says that the actual thing is being observed, right? So we write the thing here. Until here it can be given like to the null hypothesis is such not, there is no relationship between marital status and qualification. So this is will be given. So you can prove this by saying whether now this null hypothesis can be accepted or rejected is what this thing. I did the observation and got the expectation, and this expectation says that null hypothesis can be accepted. So hence H naught is accepted. There is no relationship between marital status and qualification. Yes, this is actually the case. Now let me give the third one, a very simple thing. Why? Because I want to give one more two-dimensional case. You need not solve that. Just to say me the procedure, that is enough, right? So there is actually the two things, gender and political party, right? Generally, I'm asking you a question. Is there any relationship between gender and political party? Like only males will be in political party, female will not be in political party, like that.
No, sir.
There is no relationship. But that is actually the question given here. Whether to check whether any relationship between a gender variable and a political party, right? So I'll give you some observed values. We cannot simply say no, but we can prove that using chi-square distribution, right? Based on the question, it may differ. The answer may differ. But the question has the following observed values. Out of it, and these are the observed values. And a Republic Party, a Democratic Party, and other parties. Usually, when we go to politicals, surely some other parties also will be there. Male, female. These other parties are minority parties, some small parties. So Republic Party in male we have 26, female 13, other 5, and female we have 20, 29, and 7. Right? I'm not going to ask you to solve entirely. Let that I'll do that. You do during your free time is like a homework. Now let me you say me that how you will calculate the expected value for this. How will you calculate the expected value for this? Can anyone say?
The numbers which are in columns we can consider as expected, right?
What you're saying? No, that is actually not the case. We'll be calculating something like total, right? I just have a give a recap here. I get frequency of each thing. Here also I take the frequency of each thing. How you calculated 18 expected value?
39 into
39
90
into
divided by
90.
303.
Great. Same thing I'm asking here. So here you'll be adding another thing. In question, it will not be given to you. In question, you'll be given only observed values. And in the solution, you need to write those. Solution, you need to write to this one more time. And you need to add this another column. That is this particular column you need to add. And then you have to write. So what will be writing here? Total. What is the total? 26, 29, 39 plus 5. What is this? 44. Am I right?
Yes, sir.
And what is this? 50?
56, sir.
56. Okay. And this is total. And here it is 46, 42, 12. And if you add both these things, are you getting the same value or different value? What is the value you are getting when you add all these?
100.
Both ends you should get the same value, right? Are you getting that? Yes.
Yes, sir.
Yes. Now how will be calculating this expected value for this particular table? Male to Republic. Here you have it 26 here. Instead of 26, if I want to calculate the expected value, how I'll do that?
46
Into
into
44
Great.
46.
by 100.
44
Great.
divided by
Very good.
100.
Very good. Very good. So it will be going to be 46 into 44 divided by 100. So what I'll do here, this will be equal to 46 into 44 divided by 100. So I'll do that. What is the answer for this? 46 into 44.
20.24.
Okay, 20.24. Great. 20.24. So this is the thing. Others and all we can actually directly calculate. So for 13, what I will do? For 42 into 44. 42 into 44, 18.48. Others, 12 into 44, I get 5.28. And what will be for this? What calculation I'll do? 46 into 56, that is 25.76. Here what I'll do? 42 into
42 into
56.
56.
Okay, what for? 23.2. If I do anything wrong, please say. Okay, 3.5. 12 into 56, 6.7. Have I made everything correct? Anything going wrong? Is the calculation right, pa? Then we can check by taking the total. If the total I get 100, then it means that I have done correctly. Total. What is the total? 20.24. Anyone do for the second row? 21.24. 18.48 plus 5.28. This is 44. Exactly great. 44. And what is this? Where am I getting 56 here?
Yes, sir.
It's 56. And in this total? 20 plus 25, 45. Okay, I think approximately 46 will come. Here 18 plus 23, 42. And here 12. So it is 100 again. This is the case. Quickly, if we perform, we can also get the particular values, right?